I'll put the GitHub. You know what my GitHub is? I forgot. My GitHub is Alex. It's my game time. Nothing like secret. All 2 weeks you have. No, we did have an issue with my my mutex function. I was not saying but on. But that's only if you want to. Or sorry, not then. We open up the task and then process. It creates a mutex, but it doesn't actually check it. Yeah, we open up the process. And like the create mutex thing, with like an input. Oh, that was checked. Well, no, you have to like check it at the end. Yeah, check on the check side. You have to check that you take handle. No, events are handled. I'll fix it before Friday. All right. You get to start. Yeah. We have. Give it like sign it back because I saw this. Oh yeah, like 2 people sign it. No, do I need to sign it? I don't know. On the vice president. Oh, you're here to oh, I think I get started. I can give it to one. I trust you. First presentation. This is. Oh no, we're not talking. Oh, should I talk? Because we're just gonna use this. Oh, I've always just used these.
Well, it just died. That's what it just died. That's why it's fine. Just like that.
All right, we're using a laptop mic. That's cool.
All right. You want to start us off?
Hello. All right. Thank you for coming to today's meeting. We're going to be talking about malware again, specifically going over keyloggers and sort of delving into some source code and seeing how they actually work at like the lowest level.
I get the joke. He said seeing because he wrote it in C. So it's like seeing.
Yeah.
We're not recording, are we?
We are. Yeah.
Oh wait, sorry.
Here, you want to do the plug?
Oh yeah. Become a paid member. It's $20 a semester or 35 a year. You get stuff and it's good for us and you. Yeah, all that stuff up there is probably still applicable. Before we get started, I want to give a shout out to the Cyberforce team where I think two people are here. I see two. Maybe I'm blind. Maybe, hopefully, hopefully they're coming or working. But it's a competition, right? I mean, it says competition right there. And they're flying out this Thursday to Illinois to compete against over 100 other teams. This is Cal Poly's, to my awareness, first year competing. So, you know, do you have any words for us, Jerry, Mr. Captain?
Well, thank you so much for the support. Really got us really far. So definitely appreciate that. So confident. I think
You're gonna win, right?
Thank you guys. All right, so this is just the schedule. We're here, 10:31, Keyloggers. So I'm Dylan. I'm a third year computer science major. I joined CCDC at the start of this year, and I'm trying to not be like bad at it. Um, been like applying for a lot of internships recently. It's kind of a grind, like very desperate for work. Uh, and yeah, that's my email.
Oh, what?
Did you not put your slide in?
No, I did. Yo, you gotta
Do I need
refresh
to
that.
represent?
Oh yeah. That's beautiful. I'm the other Dylan, right? And I'm not a computer science major. I'm a computer information systems, right? CIS. You can see that, right? Okay, because this thing doesn't. And I do red team stuff. The Git that's not my GitHub. That's just the GitHub link for the project today. We needed to fit it in somewhere, so I put it here. And that's my email too.
Awesome. All right, so yeah, for today, we're first going to be kind of doing an overview of malware, and then specifically how keyloggers function. And then we're going to look at the actual source code for like a pretty straightforward, I think, and like a simple example of a keylogger. And then we're going to be going into some static and dynamic analysis methods for the actual executable files of the malware. And then finally, we're going to go over methods to detect malware on a system. All right. So if you went to the meeting 2 weeks ago, you might have deja vu because I basically took the slide from that meeting and then took out all the things that I couldn't explain. So how malware works is basically there's an initial execution phase where it's embedded or malware is placed on a system in some way, whether it be a malicious executable file or like DLL sideloads, which is basically when the libraries that certain processes call to use are replaced with malicious versions of those libraries so that malicious code is executed instead of the actual code. Or maldocs, which are just like malicious like Word PDF documents that can download like viruses from the internet and then run them on a system. After it actually gets on the system and it starts running, it has the implant phase where it has to establish some sort of communication with the attacking server. Um, One way that could happen is beaconing, where the executable starts calling out, sending out a connection request to the server, or listening, where it waits from a connection request from a server, or these other like track. Do you want to explain traffic poisoning and traffic manipulation?
Yeah, those are more, how do I say, advanced functionality of malware that typically require high privileges. So this may be more prevalent in things called rootkits that have full access to the networking stack of the underlying operating system. But for today's stuff, we are using what's called user mode or lower privileged malware. So malware that doesn't have as many prerequisites for its execution. So we don't need to worry about all that extra traffic stuff yet.
Yeah. And then after that connection is made in post execution, there's a bunch of stuff that malware could potentially do, from just like stealing information like data off the system, key logging, giving like remote screen control or like remote screen viewing. You could execute commands, execute arbitrary code, move laterally throughout a network, or like hold a system ransom with ransomware. So specifically for keyloggers, some I guess key characteristics, some things that pretty much all keyloggers do is one, they have to monitor the system input in some way. Some ways that could be done would be like in Windows through thread hooks, which we'll go over and explain in more detail a little bit later, or through like more abstracted API functions. Like a lot of operating systems literally have like built-in functions that are like get keyboard, where the a program or like library or some executable can literally just see the state of a keyboard at any time. Um, they have to record those inputs in some way, whether it's converting those keystrokes to like some sort of storage in memory, or some like really scuffed examples of keyloggers that I found literally just wrote all of them into like some sort of file and just put it somewhere on the hard drive and then sent that over at some point. Um, Lots of different ways that can happen. And then finally, it has to be given to the attacker in some way. So unless the person has physical access to the system, generally it will be transmitted over the internet. Could be encrypted an encrypted data. It could just be like plain text strings of the keystrokes that are recorded. And there's like different ways that you can avoid detection during that process, such as having it request the keylog at random intervals so that the system doesn't see like regular, weird, suspicious requests. Yeah, lots of ways you can obfuscate that and make it less obvious. So we're going to now be going into the actual keylogger. It's might be a little hard to understand just because it is written in C, and we're going to be delving into the actual like code behind it. But I think it should be, you don't worry too much about like individual parts of it or like specific lines in the code, because I'll just explain how it works sort of holistically, going part by part. Yeah. So there's a few stages of my keylogger. The first is the initial execution. Basically, there is an executable file on a client system that through some means starts running, whether that's through like task scheduler, like the registry, or just like someone running it. It has to start in the system. and then it starts beaconing out to the attacking server, which then establishes a TCP connection, and the client system starts waiting for requests from the server. Then a request is sent for the keylogger to actually start recording information. And at that point, you can send requests from the server for the logs of keystroke inputs as they happen. So this is sort of an example, just like a basic example of the topology of how this works. It's pretty straightforward. There's just two systems. There's the server, which is on the bottom, the attacker computer, and the client, which is the victim computer on the top. And basically just a single TCP connection allows us to work. Okay, so this is a lot, but I'm just going to be briefly explaining what some of this means. This is the initial execution phase of the keylogger. This is the actual executable, the code in the executable that is on the system. It starts by calling this main function, which basically just defines socket variables and sets those variables to the appropriate values for the program to establish a TCP connection through its programming interface with the attacking server. So that's top left. And the next one right next to that is just showing how the IP address and ports are converted to the actual specific object types and inputs that the, I guess, socket interface and network interface needs to actually establish that connection, because obviously it doesn't just take like a plain text IP import and uses that. It has to use like specific values. And then finally, it basically just tries to connect to the server using that preset information every 10 milliseconds. And then once it finally establishes the connection, it then calls the main shell function. So at this point, we've established the connection between the keylogger and the attacking server. Oh, that's crazy. Look at my laptop. It's about to die. Where's the plug? There's one right there. That's crazy. Yeah, so then this is sort of the next part that happens after the server connects. Also, if you have any questions about any parts, feel free to ask them like at any point. This little function, bit of code on the left that's called, oh boy, what does this do? Basically just establishes some spaces in memory for important information to be held, such as the buffer, which will hold the actual plain text requests from the server, the container, which I believe holds the response input as you get response from the system, and then total response, which is the actual string in memory that's sent back to the attacking server when it is requested. And then after that point, basically how it works is if oh yeah, and then every single time a request is sent, all those places of memory are zeroed and it starts again, so that there's no issues there. Then this next part is basically just a command, basically just handling all the systems where you're not getting keylogs, but rather you're just trying to issue commands to the computer from the attacking server. Basically what it's doing is if it's a command prompt command, it gets executed in the command prompt. And if it's a specific command to request a keylog, that is handled separately. So at this point, the attacker can start the keylogger, and how that works is it's actually its own process separate from the executable. It spawns a new thread, which establishes a Windows hook. What a Windows hook is basically how Windows operating systems work is every single process, everything happening on a Windows operating system happens through, think like a virtualized thread. And what hooks do is they basically intervene or sort of step in during that the execution process of those threads and get some information or acts upon them in some way. And it's a native feature of the Windows API that's well documented online. You can read about them if you want to try and do anything yourself. And basically what we're doing here is we're setting a global Windows hook, so that means it acts on all threads in the system. And the specific hook that is being set is global keyboard input. So it's hooking all the messages, which what messages are basically just inputs from the system on Windows, and basically recording that message somewhere and then sending it where it needs to go. So every time a key press is made, the program records that key press, records that input, and then allows that input to continue to go wherever it needs to go, so that it's not obvious that it's being like stopped and intervened, right? And then at the bottom here, this is basically just showing how the actual keystroke recording happens. Basically, it just converts that key code to its appropriate character and stores that in memory somewhere. So yeah, in the diagram, keylogger hooks incoming inputs and then records them. Finally, I guess the last part is how actual requests from the server are handled, where on the right, on the right, an event is created to tell the keylog thread that the buffer is currently being read when a request to get the keylog from the server is made, so that the keylogging thread doesn't try to write or edit that space in memory as it's being sent to the attacker, because that could obviously cause problems. Basically, it also waits for any writing that's happening to the keylog to stop, and then it sends that keylog to the server and resets it to 0 so that more can be recorded and that memory is reset. And then on the left, this little function here is basically the what happens every time a keystroke is inputted. It tells the system, it tells the program that it's currently writing to the keylog. It does some stuff. It just like checks some condition, and then it waits to make sure that the log isn't being read or sent to the attacker at that moment. And then if it's not being sent to the attacker, then it's allowed to write that keystroke input to the log and then carry on. So basically, while there's keyboard input happening, we don't it's telling not to send the keylog yet because that causes issues. And while the keylog is being sent, it's telling it not to continue recording keystroke input because that can cause issues. And that's basically the main functional parts of how it works. It lots of weird looking functions, probably not very clear to understand looking at them, but I hope that you sort of have a basic overall idea of the purpose of them and what they're doing. So yeah, at this point, that code is sort of demonstrating the processes of the keyloggers sending keys from the victim computer back to the attacking server, and also the process of the attacking computer sending requests to the victim computer to get those keylogs. Yeah, so now we're going to do a live demonstration of it working.
Oh, wow, you trust the demo gods?
Yeah. Where's the... You good? Okay. I have to reshare my screen, right? Is it up? Wonderful. Okay, so right now, this is the attacking server for the keylogger. It's connected to a client that's being, I guess, recorded that has the malicious executable running on it. And as you can see, you can do things like send directory commands to get where we are in the directory, navigate through the system, like, right? It works as a shell function too, so we can actually navigate through their file system and see what it is. But also, if they type something, and we input the command, which I chose completely arbitrarily because I themed this keylogger off of they locked me in a rubber room with rats. Rats make me crazy. So all the commands are based on that. So with rats, basically gets what they've been typing. And for every reason, the victim has been typing, man, I love Dylan Tran. Ooh, I'm going to log into Instagram, instagram.com, shame, very secure password 123. And if
Wait, that's my
he types more stuff,
where'd you get my password from, bro?
and if he types more stuff and we keep requesting, wow, so cool, keylogger, very cool, well designed. It keeps getting input. Obviously, if you were an actual like attacker, you would want to sort of refine this process so that you don't have to type in the command every time you get the keylog. You'd want to have it request automatically at like random intervals. You'd want to have it stored in a file so you can access it at any point, and it's not just terminal output. But I didn't actually make this because I wanted to do like bad things with it, which is why it's just sort of a command that shows what they've typed at that moment. It's just for demonstration purposes.
For
Um,
educational
for
purposes.
educational purposes, I'm not liable for. um, yeah, I think that's enough for the demonstration.
Who up logging the keys right now? Okay, just him.
I am. Yeah.
Yeah, just him. Okay, unlucky.
Yeah.
All right.
So that's the actual explanation and demonstration portion of this. And now I think Dylan is going to take over for the next portions.
I thought you were Dylan.
You're so right.
That's so weird.
I'll just do the whole thing.
All right. We can't have a talk about malware and offensive security without talking about the mitigations or the defense, right? Never. Uh so we're gonna be going into talking about this doesn't apply directly to the keylogger. This doesn't apply exclusively to the keylogger. This is a more general approach to detecting malware. And as you will see from this sort of segment, it's kind of difficult. And there's a reason why antiviruses exist that sort of automate the majority of this process. But with that being said, static and dynamic analysis. So what static analysis is you're looking at a particular sample and looking at its static attributes, or basically what's already present when you could just look at it, right? And in this case, because we're dealing with Windows, and if we go back to 2 weeks ago where I was talking about portable executables, all executables, or the majority of executables in Windows are going to be of a file format called a portable executable. And so was his keylogger, right? That he ran, that was run to, we go back to the keylogger model, there's victim and an attacker server. The victim has to run the keylogger or the client or the implant, whatever you want to call it. That thing being run in this case is going to be an executable. And with Windows, they follow a particular file format. So when it comes to our static detection approach to this, we can sort of try to see what type of Windows API it is importing. Because remember, Windows API is how functionality of the operating system is exposed to a developer, right? So if they're importing or using a series of APIs which combined are known to do malicious activities, that's an easy way to sort of flag something as malware, right? So in this case, we're using a tool called PE Studio. Well, he did. I don't like. I haven't ever used this one, and it sort of parses that file format, right? And what we're really interested in looking at is this part of the file called the imports, right? This is where it details all the Windows APIs it's going to import. And in this case, we can see these two things, right? Call next hook X and set Windows hook XA. Oh, what?
No, you're good. Just keep
Oh, okay. So if we have any sort of background that we now do after we saw all the source code of the keylog, right? If we identify a program is importing these two what do you call it, these two functions, right? Or these two Windows APIs, that might be that this might be a reason to raise a little bit of suspicion. Why is this program creating Windows hooks, and what is it hooking into, right? There's obviously a lot more static detection opportunities that comes into and analyzing something, but many times poorly designed malware will have like 5 imports, and those 5 imports are just like something known maliciously. Like let's say in this case, call next hook and set Windows hook.
my poorly designed malware.
Oh no, this thing has 83 imports. So if you actually look through the rest, it might get muddled in the middle, right? Which is a tech what do you call it? A tactic that some malware authors will implement is to make their suspicious imports look less suspicious. They hide it within a bunch of other imports. So it just looks like, oh, just another set of two random Windows APIs being imported. There are other ways to do static detection that I don't think these slides are covering. Namely, there is something called file hashes. So every file, or not just every file, but in general, depending on the hashing algorithm, but any set of data, which includes files, has can have a hash calculated from that data. And that hash is, for the most part, unique to that particular set of data. No, a well-designed hashing algorithm will have no two pieces of data that have the same hash, right? So this hash is almost like a signature in the sense that if a known piece of data is malicious, it's going to have a hash tied to it. That hash is now tied to being malicious. So what we can do is we could check the hash of a particular sample that we're curious about and seeing if it matches a known database of malicious hashes. Once again, this is something your antivirus is capable of. And not because, I'm not going to go across all 2000 something files on my system, calculate the hashes, upload them and say, hey, is this bad, right? Antiviruses exist. Next, we have dynamic detection. So rather than looking at the executable or the sample, we're going to actually run it and see what it does. That's why it's called dynamic, because we want to see what it's sort of doing in as it runs, right? And in this case, we're for this particular screenshot, we are using something called API Monitor to look at all the Windows APIs that it is using. Realistically, this is not something you want to do as an individual, because if you notice on this top left over here, I don't know how long this keylogger was running, but there's 5,600 calls that were being made, and who knows, maybe it could be like a minute, right?
I'll go over it a little bit on Friday if you come to the workshop, but there are ways to filter for specific API calls, which is very useful when looking.
It is useful, but at the same time, sometimes you want to get all the coverage of all the telemetry you can, right? It becomes a balancing act. But me personally, I don't want to look at 5,600 API calls, see the sequence they were called in, and determine, hey, this is doing something kind of weird, right? Which is why your antivirus exists. It's capable of this now. Only took it like 15 years. There are other forms of dynamic detections, but in general, this is how it's mostly done. You just see what something's doing in runtime and sort of act upon it. Then your antivirus, while programs are running, is constantly checking what they're doing. But it also has something called like a sandbox, right? Where before you run something considered suspicious, such as something you randomly downloaded off of the internet, there may be a delay in the execution of that because your antivirus is sandboxing its execution and trying to run that suspicious executable in an isolated space to determine whether or not it's doing anything weird. And afterwards, if it gives it the green light, then it actually runs it on your on your computer. These detection methodologies aren't limited to just Windows operating systems. They are something that's employed in both Mac OS and Linux and whatever. The particular tools that we're using, though, in this case, PE Studio and API Monitor, these are limited to Windows because we're looking at Windows APIs and Windows files. But the general techniques aren't exclusive. Some more dynamic analysis techniques we can go into are network and process monitoring. It is something I talked about some amount of weeks ago, but didn't dig deep into because I was lazy. So we're going to cover it here now, right? Network monitoring. A lot of malware likes to talk over the internet because you got to transmit data somewhere, right? It's not like their attacker server is also on your machine because, I mean, you're all sorts of screwed at that point, right? Generally, an attacker is going to be remote, right? And if they're remote, they have to talk over some sort of medium. Generally, it's going to be through the internet or just remotely, right? Using the TCP/IP stack. So what we can do is we can monitor our network traffic and try to see if we find some suspicious connections, right? Connections we may deem as suspicious are weird IP addresses, although realistically, I don't know any IP address. So if I just see any of them, I'm gonna be kind of just like, oh, that's crazy, I guess. Other suspicious indications are going to be the port that's being contacted, right? In this case, we have port 50,005. I've never seen that port used in my life. So obviously, there are some pretty easy bypasses or workarounds for a malware developer, but we gotta start with the low-hanging fruit, right? Some of the obvious stuff. And in this case, the keylogger that was created is transmitting data unencrypted, so over TCP. So it's all going to be plain text. So we actually look on the bottom in the Wireshark output. You can sort of see the keylog output. So based on the keylogger model that we were discussing, I'm going to guess that the server requested keylogs, and this is the keylogger actually sending it back to the server. In this case, all over plain text, and that's kind of weird. The actual attribution of this traffic to the process, that's a task up to the attendees to figure out. Now we also have process monitoring. There's a lot of different tools that we can use for process monitoring. In this case, we're using something called Process Explorer. And you want to cover this one because I don't use Process Explorer.
Yeah, I mean, it's pretty simple. It's basically a task manager like software that was maintained independently from Microsoft for a while until Microsoft was like, oh, we kind of like this, and then they bought it. And now it doesn't come like native built in on Windows systems, but you can just go to like the Microsoft website and download it. Um, it is like the process monitor with a lot more detailed information, basically. And the specific thing that we're interested in here is that when you run it, you can enable a setting called you can enable it to connect to this website called Virus Totals, which is basically a big database of uh, known viruses and their hashes, so that it can automatically compare the hash of all the executables running in the system processes to the known hashes of known viruses. And that would be those values here on the right. Sorry, it's kind of covered by, well, you see on the right, this rightmost column is virus total. And basically, generally what you want to do is take a quick look at this. And if any of these numbers are above zero, or that could indicate that there are some parts of the executable that may be correlated to or look similar to known malware. And then also, I think in the case of, in some cases, if it's like not a known process, if it's just like some random executable, it might just say unknown because it can't really compare to anything. In which case, if you have an executable running on your system that it doesn't recognize at all, you should also probably investigate that because that's also a little sus.
Yeah. Generally, if we look on this right-hand-ish column, there's a column called company name. This is derived from something a lot of executables have, and this is across every different operating system to my awareness, is that executables or just files in general can have a certificate on them, right? Which means they were signed by a company, by some sort of entity, right? The validity of these certificates can vary, but generally, at least for Windows, Process Explorer is able to determine that all these certificates are valid ones, right? So unless the person the how should I say, the certificate signing mechanism got leaked, which is very rare, but it does happen. Generally, if something's signed, it is pretty, it's nice. If it's not signed, there's a good reason that you may want to investigate it further. Most software is signed in some capacity, like most video games that you download if you play games, or um I don't know, software suites like video editors and whatnot. Those are all generally they're signed. I haven't seen one that wasn't, unless it's just something somebody cooked up on GitHub like yesterday. It's probably not signed. But yeah, a lot of this more complicated analysis is all automated by your antivirus. Unfortunately, antivirus isn't really that good at it, so there's the caveat there. But it's good enough to catch some lower hanging fruit. I want to talk about your adventures in trying to evade Defender?
Yeah, so when I first started trying to create this keylogger, I started with this really scuffed this is like start of summer. I started with this really scuffed Udemy lesson on how to write like Windows malware, and it was horrific. Uh it like did everything like the most obvious way possible. I'm really glad that I didn't pay for it and I found a way to get it for free because it would not have been worth like any money at all to watch and follow. But basically it hit like every like it triggered every flag in Windows Defender basically. So I was like, this is useless. So what I did from there is, in order to get it not checked by Windows Defender, I worked with Dylan for like a while. And basically some ways that code like that people that make malware might do try to obfuscate their code to make it less obvious to these antiviruses what's actually going on, or they could use like alternative libraries and alternative function calls that aren't as popularly used by malicious software. In this case, initially the crappy tutorial that I followed had me just, I think it was like a it's like a built-in Windows function that you can call and see that's just like get keyboard state, which literally just returns the entire state of the keyboard. And it just had that do that on like an infinite loop, constantly getting the state of the keyboard. And Windows was like, why would any program ever do this? This is so weird. Um, and so that was one thing that triggered it. So that's why we used, in this case, the the hooking function in the Windows API instead, because that's a little bit less of an obvious malware flag. um, Another thing is potentially you might just introduce a bunch of you, because the way that I guess executables get compiled, um, they the system can detect like names of functions in them. So if you have like the system can't detect like comments because those don't get sent to the compiler. Those are ignored by the compiler. But like function names, variable names, if those are named like red flag things, the antivirus might be able to automatically detect that is malware. So that's why I had like the weird function names, like what is this doing, like fake main, like all that stuff. Another thing that you might have is just making it arbitrarily more complicated. For instance, in my case, I implemented a fake main function that didn't actually do anything, and then just called another function that called the main, which makes it a little bit harder for like Windows Defender to see like what it's actually doing. So just like it's a lot of trial and error, obviously, in terms of trying to get something to not be detected, because obviously like any good antivirus is not going to be open source, because then it's going to be like really easy to evade. So we don't really know how they work exactly, so it's just sort of trying and failing what is caught and what isn't. And yeah, in this case, this example executable that I made is not detectable by Windows Defender. It doesn't flag it as malware. But I think as we've gone over, a lot of these more manual detection methods that require some more of a manual intervention are maybe more work and a little bit more tedious, but it is very obvious when looking at some of them. For instance, the the TCP connection that just sent the plain text keylog, or in terms of the actual like looking at the executable, the dynamic detection method that you can literally just see the keystrokes getting recorded like in the call stack, are a lot easier at being able to just see what's actually going on in the case where traditional and automated antivirus fails.
Yeah, I'd still be too lazy to do that. You can have all my keys, bro. But with that being
Yeah.
said, I think that concludes this presentation. Are there any questions for us? Okay, sick. I think we can tie it up then.
All right, wonderful.
Because if I'm not mistaken, I think there's a class after this, so we should probably get going.
Oh yeah, right, yeah.
Oh,
Oh yeah, if you haven't signed in, there's a sign-in link that he's going to right now.
I gotta find
Please
it.
sign in there.
Yeah.
Very helpful. Yeah, thank you.
Thank you.
I have a feeling it wasn't too.
Oh yeah, also really quickly, the workshop this Friday is sort of going to be mostly focused on the detection skills that we went over during the second half of the presentation, where you'll be trying to find malware on a system and figure out what it's doing.
I think those are not.
Yeah.
Just figure out how to